Hi, this is homework chapter 9, and it will be solving problems 1, 3, 5, 11, 21, 25, 45, and 53. Let's get going with this. All right, problem 1. 1A reads, what angle in radians is subtended by an arc of, so arc, that's S, equals 1.50 meters along the circumference of a circle with a radius 2.50 meters. So R equals 2.50 meters. So our formula is the arc length equals the angle in radians times the radius. So we want to know the angle in radians. That's going to be equal to S over R. It's going to be equal to 1.50 meters divided by 2.50 meters. That's going to be 0.600 radians. Now, if we want to convert that in degrees, we know that pi radians equals 180 degrees. So let's do this. Pi times R So I have 0.600 times 180 divided by pi is going to give me 34.4 degrees. I think that was the answer to B. Oh, that was A part 2. A part 2. Okay, part 9.1b asks, an arc length of 14 centimeters, 14.0 centimeters, long on the circumference of a circle, subtends an angle of 128 degrees. Theta equals 128 degrees. What is the radius of the circle? All right, R equals S over theta equals 14.0 centimeters divided by, I've got to do that in radians, 128 degrees times pi radians over 180 degrees. And that will give us 6.27 centimeters. Okay, now finally question C says, the angle between two radii of a circle with radius 1.5 meters is 0.700 radians. What length of arc is intercepted on the circumference of the circle by the two radii? So S is going to be equal to R theta. S is going to be equal to 1.50 meters times 0.700 radians, and we're going to get 1.05 meters, and that is problem 9.1. Number 9.3 says, the angular velocity of a flywheel obeys the equation omega t equals A plus B t squared, where t is in seconds and A and B are constants having numerical values 2.75, this is 2.75 for A, and 1.50 for B. A, what are the units of A and B if omega is in radians per second squared? So A, we need to know units if omega is in radians per second squared. So A is going to be radians per second squared, and B is going to be radians per second to the fourth. Oh, pardon me, I misread that problem. It says, what are the units for A and B if omega is in radians per second? Therefore, this A is going to have radians second, and B is going to have radians per second cubed. Okay, and that's 9.3a. Okay, for B wants to know what is the angular acceleration of the wheel at t equals 0 and at t equals 5 seconds. So for B, d omega dt is going to give you alpha. It's going to be 2bt. All right, so 2b is going to be equal to 3 times 1.50 radians per second cubed times t. And let's see, we're asked for t equals 0. Well, that's going to be 0. And t equals 5. And for t equals 5, we're going to have 5 times that. That's going to be, let's see, T2, let me make sure I get this right. T2 is 5 seconds, 5 times 1.5. Anyway, I think I just made another mistake here. That's going to be 2bt, so it's going to be 3.00 over seconds cubed times 2 seconds. That's going to be this is 5 seconds. 5 seconds, not 2. This is going to be equal to 15 over seconds squared. All right, finally, we are asked through what angle does the flywheel turn during the first 2 seconds? Now we've got to integrate. So we've got delta theta, or d theta is going to be delta theta, I'm sorry, is going to be equal to from 0 to 2 seconds of a plus b t squared dt. So that's going to be a of t plus 1/3 bt cubed from 0 to 2. And we have our values. Let's see, we have a as being 2.75. So we have 2.75 radians per second times 2 seconds plus 1/3 times 1.50 radians per second cubed, was it? Yes, cubed, also times 2 seconds. And then that's quantity cubed. This is going to give us 9.50 radians. Okay, 9.5. Hi, everybody. This is 9.5. We've already done 9.3, 9.5, which reads, we have done 9.3, yes? Yes. A child pushing a merry-go-round. The angle through which the merry-go-round has turned varies with time, according to theta of t equals gamma t plus beta t cubed, where gamma equals 0.400 radians per second, and beta equals 0.0120 radians per second cubed. Okay, so calculate the angular velocity of the merry-go-round as a function of time. What is the initial value of that the angular velocity? That's it, when t equals 0. And calculate the instantaneous value for the angular velocity at t equals 5 seconds. Okay, so the angular velocity at any given time, omega, is going to be equal to d theta dt. And that's going to be equal to gamma plus 3 beta t squared. Okay, and we have those values for gamma and beta. All right, at t equals 0, am I supposed to find, let's see, calculate the instantaneous angular acceleration. No, I'm sorry, that's number 9.4. What is the initial value of the angular velocity? Okay, so I'm just going to put this in there. At 0, it's going to be this. 0, so for B is 0.400 radians per second. That's the initial velocity at t equals 0. And finally, calculate the instantaneous angular acceleration at t equals 3 seconds. Oh no, that's 9.4, sorry. C is calculate the instantaneous value of the angular velocity at t equals 5 seconds and the average angular velocity for the time interval t equals 0 to t equals 5. All right. For my instantaneous angular velocity, I just have to plug in 5 seconds here. So I'm going to get 0.400 radians per second plus 3 times 0.0120 radians per second cubed times 5 seconds quantity squared. And let's see if I can snag that answer here. I'm going to get 1.30 radians per second. So omega at t equals 5 seconds equals 1.30 radians per second. Now, for my omega average, this is going to be delta theta over delta t, and delta theta is going to give me, let's see, 3, this times 5. Oh, let me pause and get myself some board space. Okay, so we're going to have, let's see, delta theta is theta final minus theta initial. And that's going to give me for whatever average angular velocity for t equals 0 to t equals 5. So for t equals 5, we're going to get 0.400 radians per second times 5 seconds plus 0.0120 radians per second cubed times 5 seconds quantity cubed. And that's going to be 3.50 radians. So theta at 5 seconds equals 3.50 radians. And then theta at 0, we've already determined that. Theta at 0 would be 0. Theta at, we determined omega at 0 is 0. So we're going to have 3.50 radians minus 0 over 5 seconds minus 0. And that is going to be 0.700 radians per second. So the average is not going to be the same as the instantaneous, as you can see right there. That was 9.5. 9.11 reads, the rotating blade of a blender turns with constant angular acceleration of 1.50 radians per second squared. So alpha is going to equal 1.50 radians per second squared. How much time does it take to reach an angular velocity of 36 radians per second? So we want to go from 30, omega final is going to be 36.0 radians per second. And omega initial equals 0 radians per second. And we can do this like we do those kinematic expressions where we have omega final equals omega initial plus alpha times time. So let's see, we've got 36.0 radians per second minus 0. Oh, plus, I'm sorry, that's plus. Equals 1.50 radians per second squared times t. And if I do the math on that, I'm going to get 24 seconds. Okay, that was 911 part A. Okay, 911 part B wants to know through how many revolutions does the blade turn in this time interval? Well, we're going to solve it for the radians, and then we'll convert to revolutions. So we know theta final equals theta initial plus omega t plus 1/2 alpha t squared. And let's see, we have starts from rest, and that's 0. So omega final is going to equal to 1/2 times 1.50 radians per second squared. And I believe that was 24 seconds. Yes, 24 seconds quantity squared. And this is going to give me 432 radians. And 1 revolution equals 2 pi radians. So if I want to take 432 radians, I want to convert to revs over 1 rev divided by 2 pi. I am going to get, let's see, 68.8 revolutions in 12 seconds. That's a nice blender. That'll whip you up some nice whipped cream. And I'm hoping that you guys can see the similarity between the rotational kinematics and the linear kinematics. Yeah, just learn those equations real well, and you can just substitute the rotational terms. But anyway, 9.21 reads, a wheel of diameter 40 centimeters, 40.0 centimeters, starts from rest and rotates with a constant angular acceleration of 3.00 radians per second squared. So R is that, alpha is 3.00 radians per second squared. Compute the radial acceleration of a point on the rim. 1 minute. I'll be back. Okay, I had a phone call there. Took a little while. I got a little interrupted. I don't remember where I was, so I'm just going to start number 9.21 again, and just bear with me, everybody. A wheel of diameter 40 centimeters starts from rest and rotates with constant angular acceleration of 3 radians per second squared. Compute the radial acceleration of a point on the rim for the instance the wheel completes its second revolution from the relationship A radial equals omega squared R. And B, so we do it both ways. In B, A radial equals B squared over R. Okay, so now we're going to find omega by this omega final squared equals omega initial squared plus 2 alpha delta theta. And we are asked to find it for the wheel completes its second revolution. Okay, so we have omega final squared equals 2 times alpha, 3.00 radians per second squared, times delta times theta. Delta theta is 2 times 2 pi radians, because 2 pi is 1 revolution. We've got 2 revolutions. So there we go. Taking the square root of both sides, and I'm going to get omega final is going to equal to, let's see, 8.68 radians per second, 8.68 radians per second. Now, to do the first one, A, I've got to convert that centimeters into meters. So we've got 8.68 radians per second, and that's quantity squared times 0.4 meters. Okay. And A is going to give me, oh wait, is that diameter? Wait, is wheel of diameter. Okay, so I've got to change this to 2. I want the radius. So that's the diameter, sorry about that. So the radius is going to equal to 0.2 meters. All right, and anyway, from this, we're going to get 15.1. Oh, no, so, whoa. Oh, A radial. So A radial is going to be 15.1 meter per second squared. Now, let me pause and clear. Okay, and we know that V equals omega R. So V is going to be equal to 8.68 radians per second times 0.2 meters. So V is going to give me 1.74 meters per second. All right, now V squared over R, A radial equals V squared over R. That's going to give me 1.74 meters per second. Quantity squared divided by 0.2 meters, and that's also going to give me 15.1 meters per second squared. And that was 921. 9.25 is a centrifuge and reads, an advertisement claims that a centrifuge takes up only 0.127 meters. 0.127 meters of bench space, but can produce a radial acceleration of 3,000 Gs. So A equals 3,000 Gs at 5,000 revolutions per minute. So V is going to be equal to 5,000 revolutions per minute. A lot of conversion to do here. Anyway, this is D, so you got to have that, because if it's spinning and it only takes up that much bench space, I'm assuming that that's the full diameter. Calculate the required radius of the centrifuge. Is the claim realistic? All right, so we'll do that. Okay, so we know that A radial equals R omega squared, but we got a lot of conversion to do. So we've got 3,000 Gs times 9.8 meters per second squared. We're going to get a radial of 29400 meters per second squared. And omega, we got to convert that too, because we've got 5,000 revolutions per minute. So we've got omega, it's going to be equal to 5,000 rev per minute times 2 pi radians per rev, and times 1 minute over 60 seconds, right? 60 seconds. And this is going to give me, omega is going to equal to 523.6, 523.6 radians per second. Okay, all right, so now we'll just go ahead and do our math. So we wanted to know the required, required radius for this. So R is going to be equal to A radial over omega squared. It's going to be equal to 29400 meters per second squared divided by 523.6 radians per second, quantity squared, and I'm going to get a radius of 0.107 meter. So it can't be true. It can't. That twice this is 0.214, and they're claiming that. So something's up in the mix. Something's not going on right here. Anyway, it's a good problem. A lot of stuff, a lot of details in that problem. Okay, well now we're on 9.45, which reads, a thin light wire is wrapped around the rim of a wheel. The wheel rotates without friction about a stationary horizontal axis that passes through the center of the wheel. The wheel is a uniform disk with radius r equals 0.280 meters. An object of mass m equals 4.20 kilograms is suspended from the free end of the wire. The system is released from rest, and the suspended object descends with constant acceleration. If the suspended object moves downward a distance of 3 meters in 2 seconds, what is the mass of the wheel? So delta x equals 3 meters, and delta t equals 2 seconds. So we need to know the mass of the wheel here. Okay, first we're going to solve for that velocity of the wheel. So we're going to use the handy dandy delta x equals 1/2 v naught plus vf times t. So we know delta x is 3 meters equals 1/2, and v naught is 0 plus v final times t. So I did just to solve for v final. So 3 meters times 2, and t was 2 seconds divided by 2 seconds. And that will be 3 meters per second, right? 3 meters per second. Okay, with that in mind, I can solve for the omega of the wheel. So what do I know that, let's see. I've got v equals omega r, and we've got omega is going to be equal to v over r. So this is v of the block, and omega of the wheel is going to be equal to 3 meters per second divided by 0.280 meters. And that's going to give 10.71 radians per second. Okay, that's omega. Then we're going to use conservation of energy. So what happens? We're trading in that potential energy. mgh for 1/2 mv squared plus 1/2 I omega squared. And what are we solving for? The mass of the wheel, right? I need to find out what I is. So the I of a disk. Let's see. Okay, I'm going to go ahead and do this. So I have mass, yes. All right. I'm going ahead and I want to solve for I. I'm going to have mgh minus 1/2 mv squared times 2 divided by omega squared is going to give me I. So let's go ahead and we've got 4.2 kg times 9.8 meters per second squared times 3 meters minus, I better get a little board space here until I'm going to run out, minus 1/2 times 4.2 kgs times V is 3 meters per second quantity squared times 2 over 10.71 radians per second quantity squared is going to give me I. And I is going to be equal to 1.824 kilograms times meters squared. All right. Now, that's what my moment of inertia is. Let me get a little more board space. And that wheel is going to be a solid cylinder. So we've got 1.824 kilograms times meters squared. That's a solid cylinder. And a solid cylinder is 1/2 mr squared equals 1/2 mr squared. So I'm going to go ahead and solve for m. So I've got 1.824 kilograms times meters squared times 2 divided by the radius, which is 0.280 meters, is going to give me a mass of 46.5 kilograms. And that's a real good problem. You can understand that when you're really doing well, you're really ahead of the game. All right. Problem 9.53, it wants you to calculate the moment of inertia of a solid disk, and it's long, and I want to refer you to example 910. Example 910 has this whole thing done. One thing that might be a little confusing is R2 to the 4th minus R1 to the 4th is going to give you actually it doesn't not omit that step. That step is right underneath the next one, but it's R2 squared minus R1 squared times R2 squared plus R1 squared. So that's just a little identity you probably should know. But it would be very insightful to go through example 910. That's 9.53. And also you could check on that Zoom meeting homework posted on your Canvas. I have gone through that whole derivation of this problem in that prior Zoom meeting. At the end of the meeting, it's all in there. So you could listen to that, or you could go through this. Or you can ask me during Q&A, we could go through it together. But I'll leave that to your pleasure for now. All right, chapter 9.